Morning, folks. Sorry for the slight delay in getting started. I appreciate those, I don't know how many, like 3, 4 of you that have tuned in early. And those of you who are continuing to turn in, I appreciate it. I apologize for the inconvenience. There will be 3 more lectures like this that I have to start a little early. It's just because, you know, during the regular semester, they schedule my courses back to back in the fall, and unfortunately, 10 minutes is not time to get a digitally proctored exam set up, so I have to start these a little bit earlier. One of the perks of doing the exams the way we do them in this class is that I don't have to worry about that, and neither do you. So I guess count yourself lucky in that regard. Don't count yourselves lucky because, of course, our exams are difficult. With that said, today we are moving on. We are finished with capacitors for now. We will come back to them again at the end of Unit 2. But for the time being, we are moving on. Specifically, we are going to be moving on to the topic of electric current and resistors. Now this, oh good, my slides work. This is the behavior when we go from circuits that are in equilibrium. So that means there are no net electric fields or anything. All of the charges are nice and comfortable and at rest in all of the circuits we've discussed so far. We are now moving into a regime where the charges are allowed to move around, and importantly, the electric field is not going to be zero anymore. We call this the difference between equilibrium, where electric field is zero inside of a conductor, and non-equilibrium, where that electric field is non-zero. Well, wait a minute, Professor Coyne, you said a long time ago that the electric field was always zero inside of a conductor. And that is true for conductors at equilibrium. Now we are imagining specific scenarios wherein we take something like a battery that provides a voltage difference, which we then connect via conducting material, and that process is going to create a non-zero electric field inside of the conductor. So this is a fundamental departure from what we've been talking about so far. Up until this point, everything we've discussed has been the case of equilibrium. Now we're finally opening ourselves up to the possibility that this electric field is non-zero, which will cause the motion of charge. Because, of course, if there's an electric field inside a material and there are charges in that material that are free to move around, pardon the background noise, a dehumidifier just kicked on. If there are charges that are free to move around, then they will experience a force from this electric field. Positive charge will feel a force in the direction of the electric field, whereas a negative charge will feel a force in the opposite direction. So we're going to see that these non-equilibrium conditions lead to charge carriers that are free to move around, and this is going to produce something called electric current. Anytime you have charge moving through a circuit, well really, whenever you have charge moving in general, but we're specifically talking about circuits, you have what is called an electric current, which is a net flow of charge through a region per unit time. So if you imagine, if I'm just sitting on the side of the highway, right, and I am counting how many cars pass me. I have cars going in one direction in one lane, and cars going in the other direction in the other lane. Those correspond to the direction of positive and negative charges. Well, when I'm measuring the current, what I'm effectively doing is I'm just counting how many cars pass me in each direction. 1, 2, 3, 4, 5, 6. I'm just counting up how much charge moves past the point that I'm looking at. I then just divide that by the amount of time it took me to measure those things, and I get the current. Note that if we're doing this carefully, this isn't just a total amount of charge and a total amount of time. It's actually a derivative. It's a rate of change of the charge with respect to time, because these things may be moving at non-constant speeds and at irregular intervals. So we define our electric current, note that we use the symbol I, as dq dt. It's the derivative of charge with respect to time. Now, we can read the unit of current right off of this equation. It is charge per time, so that is coulombs per second. But we give a special name to the coulomb per second unit. We call that 1 ampere. And so current is measured in amperes. With that said, you might also hear me refer to it as the shorthand version of just amps. And in fact, if you have ever done any sort of electrical work in and around your house, you'll notice that most circuits in, say, for example, your circuit breaker are labeled with an amperage, generally 15 amps or 20 amps. That's the maximum amount of electric current that your circuit is able to handle without too much issue. You'll also notice if you take any piece of electronic device, this is a wireless charger for a cell phone, generally on the back or on a corner or on a label somewhere, it will give you a few numbers. One of those will be the input voltage, and importantly, it will also tell you the input and output amperage. This in particular takes 5 volts in at 2 amps and puts or 9 volts in at 1.67 amps. So that's telling you how much current goes into your device. And we're going to find out that electric current has lots of rules that govern how it behaves. In order to really understand those, though, let's try to talk about a sort of physical scenario where we might actually have charge moving. To that end, let's imagine a pipe, a regular, plain old pipe. And that pipe has fluid in it. Particularly, it has an electrolytic solution that has some positive ions and some negative ions. This is very common. The tap water that comes out of your faucet has some ions in it, usually something like sodium and maybe some chlorine for a little bit of, what's the word I'm looking for? Anyway, cleaning the water out a little bit. Sterilization, that's the word I was looking for. And so this might represent a common scenario of water with some ions flowing through an actual pipe, the sort you would do plumbing with. Now, if we imagine that pipe is our material, is our conducting material, which is perfectly fair. It's got ions in it. Those ions are free to move, so it's got charge that's free to move around, so it can conduct electricity. And we are going to apply an electric field to this. Well, right away, we know any positive ions, for example, sodium, are going to feel a force to the right in the same direction of the electric field. And we can get the other charges, the negative ones, they're going to be moving to the left because they feel forces in opposite directions. Now, if we wanted to just count up how much charge moves through, say, this cross-sectional area of the pipe, in this case, it really is as simple as counting. We take n, the number of positive ions, times the amount of charge on one ion, multiplied by the speed at which those ions are moving. Because obviously, if ions are moving very slowly, the current's going to be very low. But if the charges are moving very fast, the current is going to be high. Now, this first part of this counting exercise, where I'm just taking the number of charges, the amount of charge on each of those, and the speed at which they're traveling, this multiplication just tells me how much current is moving along a line, but it's independent of time. So if I start my stopwatch and it doesn't take I just give it a second, let's say, I'll count a little bit of charge. But if I let my stopwatch run for 10 seconds while I'm counting, I'll count more charge. As a result, I also have to take time into account. Finally, like I said, this is all about charges moving along a line, but I have a pipe that has more than one dimension. It has length and width. So I need to multiply this by the area of the pipe to get the total amount of current that's moving through here. And we can check that these units work out. N is just a number that has no unit. Q has units of coulombs. Velocity has units of meters per second. One thing I actually want to say is I misspoke slightly. This goes back to discussions we had back in Unit 1. We use capital N to represent the actual number. So that's like 1, 2, 3, 4, 5. This is in contrast to lowercase n, which is the one being used down in this equation, which is the number density. Specifically, lowercase n is capital N divided by the volume. It's a subtle but important difference because that's going to give us units of m cubed down here. So n is the number density. It's 1 over meters cubed. Q is coulombs. V is meters per second. T is time. So that's in seconds. Area is meters squared. And sure enough, the S cancels out. These combine to give me a factor of meter cubed, which cancel out with these. And so the unit I'm left with is charge, coulombs. So sure enough, this expression is just the amount of charge that moves through this area in the pipe. Now, if I want to be very careful and I want to do this with, calculus instead of, just counting, I need to be careful. I need to look at which ones of these variables really depend on sort of infinitesimal changes. Most of this stuff is just constant, but time is the odd person out. And so what I'm actually going to do is I'm going to label my time as just an infinitesimal amount of time. So I keep my stopwatch open for a very, very short amount of time as I'm counting. So once I'm here, I recognize that this will give me the number of, say, sodium ions through the area. But in this particular example, I have more than just the sodium ions. I also have the chlorine ions. So you'll note that when I add up the total amount of charge here, I have two terms. One from my positively charged ions, and another one from my negatively charged ions. And this gives me the total amount of charge, which I'm calling dq, that passes through this area. Now, it may be a question why I'm going through this exercise, but ultimately it's for two reasons. First, it's so I can write down an actual expression for the total amount of current in a scenario like this one. Current was defined as the derivative of Q with respect to time, so I just take this expression and I divide it by dt. Note the dt goes away, because it is in both terms. As a result, I just get this value down here. This, in turn, allows me to define a second quantity called the current density. The current density, J, I want that to be in red. I'm going to do this with magnitudes for now, is equal to the current divided by the cross-sectional area of the wire. This is because this expression here, which is the current in the wire, depends on the geometry of the wire. A larger pipe will have more current. This is not convenient for us. In general, we don't want to have dependence on the wire when we're doing problems like this. And so current density, we divide that area out. This gives us something that depends only on the motion of the charges themselves, which is arguably the more important underlying physical process. And finally, this relationship down here gives us the way to go back and forth formally between the current, which is a scalar value. Current is a scalar. It does not have vector direction, versus the current density, which depends on the velocities of the charges, so that is, in fact, a vector. And so there's a dot product here. This gives you the relationship between magnitudes. This gives you the way to go from the vector current density to the current. So that was reason one. Reason two is if we look at this equation closely and we consider all of these terms here, specifically, let's consider the current density down here. You'll note that for this scenario, these two terms, N1, Q1, V1, N2, Q2, V2, note that because these are in a vector equation, this will give us explicitly the direction of the charges. And so consider, for this example that we're going through here, Q1 is positive, and V1 is in the positive I hat direction, right? Because over here, V1 is to the right. So this first term here, and I realize the way I wrote that is a little bit confusing, is positive. This first term is definitely positive in the I direction. If I compare that to this second term, note that my Q is now negative, and my velocity is now in the negative I hat direction. These two negative signs cancel out with one another, so this term is positive too. Even though these charges are moving in opposite directions, they produce current densities that are in the same direction. This is actually a very important result. No matter what the sign of your charge that's carrying the current, so if you have positive charges that are moving in an electric field, they would move to the left, and that would produce a current density to the left. If you had negative charges moving instead, they would be moving in the opposite direction with the same applied field, but they would still produce a current density to the left. And so we would indicate, if we were just talking about current in the sort of general sense, that in both cases, current flows to the left. So I realize that's a little bit confusing based on what's written on the slide, so instead I'll just leave it in terms of charge density. So the takeaway here is no matter what's doing the moving, no matter if it's the positive charges or the negative charges, the current density and therefore the current will ultimately be in the same direction regardless. And this is going to come into effect later when we start talking about circuits. Before we get there, however, we need to now talk about the actual process of current flowing through a material. Because, as one might imagine, this is not an effortless exercise. It takes energy to get these charges moving, and then it takes energy to keep them moving. And that is because, in general, while conductors allow for free movement of charge, it doesn't allow for effortless motion. And different materials are easier or harder to move charge through. We can quantify that behavior by talking about materials' resistivity, its resistance to, the conduction of charge through its stuff, or rather through its actual, bulk properties. To that end, what we're actually going to want to discuss here is a new circuit device called a resistor. And that's what we are talking about on this slide. Now, a resistor is an incredibly simple device. It is just a block of conducting material. It has two ends, so it has two terminals, so the wires will stick out both ends of this device. But otherwise, it is just a block of material that charge can flow through. Now, this device, the resistor, has a property called the resistance. This is an attribute of that specific device that quantifies how difficult it is to get current flowing through it. Higher resistances produce lower currents for a given voltage because those devices do not conduct electricity as well as, say, a wire might. But whereas the resistance is the property of a specific device, meaning a device with specific geometry, with a specific shape, you can also quantify the behavior of the conducting material that the device is made out of with another property called the resistivity. So if the resistance is an attribute of the specific device you're using, the resistivity is an attribute of the material that that device is made out of. So there is a subtle but important difference there. Now, we define resistance in a very straightforward manner. We take an applied voltage and we measure how much current that produces. The ratio of the applied voltage to the current that is produced is the resistance of that device. So if I attach a resistor to a 9-volt battery and I get 2 amps of current, my resistance would be 9 divided by 2, or 4.5. Now, we can do some other things with this to define other properties. The only one I really want to emphasize, other than the resistance, which note we use the symbol R, and it's worth noting that the units are volts per ampere, and we give that a special name called the ohm, and we use the Greek letter omega to indicate that. So the unit of resistance is ohms. For the resistivity, instead of dividing the voltage by the current, we instead divide the electric field by the current density. And that's going to give us the resistivity of the material. The reason being is that the electric field and the current density are independent of the shape of the device. It depends only on the material itself. Now, this is somewhat confusing. For resistivity, we use the Greek letter rho. And if this looks familiar, it's because we have used it before. This use of the symbol rho is not the same as the volume charge density. The unfortunate reality is that we in physics have many different quantities and concepts that we need to represent using variables. Unfortunately, there are only so many symbols available for our use, so we do reuse them sometimes. Note that we also use V for volume, capital V for volume. We also use I for the moment of inertia. We use rho here for both the resistivity in unit 2 and the volume charge density in unit 1. Similarly, if I take the resistivity, which again I want to emphasize is a material property, and I take its inverse, so I do 1 over the resistivity, I get a different measure, which is called the conductivity. So if the resistivity is a material's inherent or innate resistance to the flow of current, the conductivity instead measures how good of an electrical conductor it is. So similarly, this sigma is not the surface charge density. We reuse these symbols here, and so you have to keep them straight in your mind. You have to be very careful that you're not mixing them up because they're very different things. Now, the good news is that more or less, whenever you're doing Unit 2 problems, these are the only ones that you'll end up using, the resistivity and the conductivity. You'll never have to worry about these charge densities when we're doing Unit 2 problems for the most part. And this is because these charge densities, those were defined in terms of equilibrium, and we are no longer in equilibrium. So we're safe to reuse those symbols. But if you're doing like formula hunting on a formula sheet, you do want to be careful. And finally, we can relate the vectors to each other, meaning the electric field vector and the current density vector, via these relationships here, but those are not as important as the rest. So I just want to box real quick these equations because they are all relevant to our purposes in this course. Okay. So again, all conductivity is a measure of how effective an electrical conductor it is, material is. So if something has a low conductivity, it does not conduct electricity well. If it has a high conductivity, it will conduct electricity well. This is in response to a question in the chat, by the way. So if you have ever talked about conducting electricity, colloquially, like using, say, copper wire, the age-old adage of don't stick a fork in an electrical socket, that whole idea, that's because those metals are highly conductive, so they would have high conductivities. This is in contrast to, say, most insulating materials, where you would in fact see very low conductivities because they have very high resistivities. In fact, you can see that in this table right here. This is a list of resistivities for different materials. Up at the top, I'll zoom in here so you can see the numbers. You'll notice that common conducting materials like copper or aluminum or tungsten, they have resistivities, say, of order 10 to the minus 8. So this means they have very, very low resistivities. So they have low resistivities, which means they would have high conductivities. So these are all highly conductive materials because their resistivity is small, therefore their conductivity, which is the inverse of this number, would be very high. By contrast, if you look at these materials down here, things like silicon, wood, glass, rubber, amber, they have, well, particularly down here, enormous resistivities by contrast, as high as 10 to the 16. Note that that is 24 orders of magnitude removed. These all down here have high resistivity, therefore they have low conductivity, and that's what marks these as insulators. Note that there is not a firm line. All of these materials, even though they are insulators, they still have a resistivity. Reality is not always as neat as we would like to think when we do our highly simplified models. And in fact, there would be a threshold somewhere in here that would kind of mark the difference between an effective conductor versus an effective insulator. The one thing I do want to mention about all of these resistivities, though, is that they actually depend not only on the material, but also the temperature that the material is at. In fact, you'll note that this column here of the resistivities is specifically the resistivity at 20 degrees Celsius, or approximately room temperature. In fact, not only do these materials have a resistivity, there is also a temperature coefficient, we use the symbol alpha to represent that, that indicates how the resistivity changes at other, as temperature changes. So it's this formula right here that gives us the relationship between the temperature coefficient alpha and the resistivity at different temperatures. So this rho sub 20 is the value from this column. Tc is the temperature of your conductor at, in Celsius. So if, say, I wanted to know how this was going to work at freezing, I would plug in 0 here. If I wanted to know how it worked at 97 degrees Celsius, I would plug in 97 degrees Celsius. But it's important that this temperature is in Celsius. And then finally, this row here without the subscript is the resistivity at this temperature. And that's all indicated here. This formula only works for temperatures near to 20 degrees. So this will not work at 1,000 Celsius, in no small part because at very high or very low temperatures, these materials will change state. They will either freeze or they will melt, depending on what they are. Most of these are solids, so they will melt, or at least they will start to behave differently. So we just use this equation for the sort of standard operating range of temperatures. So you might imagine something like 0 to 40 degrees Celsius or something like that. So keep in mind that resistivity is a material property, so it depends on the material, and it also varies as a function of temperature according to this equation. Okay. Now, how do we know when something's a resistor? Easy. If its voltage is proportional to its current, that is to say, our definition of resistance was V divided by I. If I rearrange that, I get V equals I times R. And so if the voltage across a resistor is proportional to the current, and that constant of proportionality is the resistance, then the object is a resistor. So basically, if I plot voltage versus current, and I get a nice straight line that goes through 0, then that device behaves like a resistor. Note that the symbol we use for circuit components that are resistors are these jagged lines. We'll see more of that in a little bit. For example, this might be different than the behavior of a different device. Here is a plot of potential difference versus current for a device called a diode. Now, you don't need to understand how a diode's working, although I will mention that diodes are, for example, the things that are running your LEDs if you have LED lights. The backlight of your computer screen, probably using very small LEDs. If you have a regular plain old television remote control, which I have. That's weird. Anyway, I'll use this one. If you have a little, remote control and there's a little, piece of shiny plastic in the front of it, chances are there is a diode in there that, in fact, you can see lighting up right there. That little dim light is an infrared diode. So these diodes, again, you don't have to know how they behave. All you need to know is that if you were to plot their current versus potential difference, it would look like this. And this graph does not look like this graph. Therefore, this device is not a resistor. This V equals IR is very fundamental. We call it Ohm's law, and it gives us the relationship between voltage and current through a resistor. So if you recall from our previous lectures, when we were talking about capacitors, we used C equals Q divided by V as our kind of fundamental relationship for those capacitors. Now, for resistors, our fundamental relationship is going to be Ohm's law, V equals IR. So we're going to see this coming up all the time for the remainder of this unit. Now, if we wanted to actually calculate the resistance of a specific device, so this is, say, like I have a wire or a resistor, and I want to calculate its resistance, I can do so from the resistivity of the material that I make that device out of. For example, most household wiring is made out of copper. And so I would go find the resistivity of copper. I would measure the length and area of my wire. And for a uniform cross-section, so that's assuming everything is nice and stays in the same shape, I can get the resistance of that wire by using my relationships between current density and current voltage in the electric field, and then just applying Ohm's law. And when I do, for a uniform cross-section wire or a uniform cross-section resistor of any kind, I get that my resistance for that specific device is rho times L divided by A. I like to think about this as a resistor design equation. So in the same way I had capacitor design equations that were a way of measuring the capacitance using only the physical dimensions and the physical properties of the device, this is a way of getting the resistance using only the physical properties of the device. And it's worth noting that when we say resistors in this class, we're generally referring to specific devices. But real, everyday, actual, realistic wires, they have resistance as well. And so this is, a common feature. What we're going to see later on in this section is that we're going to treat wires as ideal, meaning we're going to pretend like their resistance is 0. And that's just because, generally speaking, the resistance of a wire is a very small number when compared to the things that you plug into it. So just keep that in mind. Well, more on that on Friday. It's worth noting, though, that this equation assumes a uniform cross-section of wire, but the wire doesn't have to be uniform in cross-section. I could have any sort of strange shape that I like. The only problem there is then I have to use this equation, but I have to use it over an infinitesimal slice of this wire. So I have to take my resistivity, I multiply it by the length, where instead of L, it's dx, and then I divide it by the area at that specific place. So if I zoom in here, you see I'm taking a slice of width dx and I'm calculating the area at this specific location. And then once I have that, I need to integrate this over the length of the wire. And so for wires that do not have constant cross-sectional areas, I have to use this integral form of this equation here. This is the more general result. Note, of course, that I can get this equation from this if my area is constant. Then I can pull it out of the integral. And of course, the integral of dx is just x, which I then evaluate from 0 to L. And so, of course, I just get rho L over A. So realistically, this is a special case of this. This is just an example of an application of that. Here we have a coaxial cable where instead of having current traveling down the length of it this way, we're assuming the current is going from the inner surface to the outer surface. And so we could calculate the resistance of a device in this configuration by taking my resistor design equation, plugging in the area of this surface of the cylinder, and then just integrating from the inner radius to the outer radius. And we see here, we get a strange sort of equation for the total resistance of the wire in this configuration. Stuff like this is pretty uncommon, but take a look in the lecture notes that have been uploaded because they will be, that will go through this in a little bit more detail. All right, let's see. I got 1, 2, 3 slides left. One of those is the quiz, so let's just talk about this real quick. These two are kind of examples. I know we've been talking about it. We've been making a lot of vocab definitions and stuff, so let's actually do a little bit of work. Now here we have a steady current that is flowing from left to right. So I1 goes, so the current comes here, the pipe widens, or the wire widens, and then the current splits down here. Now we want to rank the current densities in the 3 segments. And we're going to get to rules We're going to get to the specific rules that cover how current behaves in future lectures. But for now, we can actually use our intuition to kind of make some intuitive arguments for this. And we're going to do so by relating this to, like, again, water flow through a pipe. If I have a pipe and I'm, say, pumping a gallon per minute through that pipe, then if my pipe widens or or gets narrower, then, you know, the water doesn't go anywhere. I mean, it still stays in the pipe. It's still flowing through the pipe. So if I start off with 1 gallon per minute, I'm still going to have 1 gallon per minute here, even though the pipe is wider. And so this represents a sort of continuity condition or a conservation relationship for the amount of charge. The current is always going to be the same everywhere in a single contiguous wire. Current is the same everywhere in a contiguous wire. So for example, I'm just going to draw a dotted line here. Prior to this point in the circuit, I am classifying my wire as contiguous, meaning yes, it gets wider, but it remains just a single wire. This means that my current 1 is equal to current 2. Similarly, current splits at junctions. Might help if I could spell. So the current that is coming through this wire here, when it gets to this point, some of it is going to go up and some of it is going to go down. Now, for our purposes here, we can estimate the amount of current just by looking at the size of the pipe. It stands to reason, if the pipe is of equal size, then each one of these little branches will get equal amounts of current. So similarly, we can assume I3 is equal to I4, and that those are each equal to 1/2 of the original current. Or let's make that I2 to be consistent with the notes. So if I were to rank the currents, I1 is equal to I2 is greater than I3, which is equal to I4. But of course, that's not what this problem is asking. This problem is asking for us to rank the current densities. Now, to do that, we need to calculate the current density at each one of these points. J1 is I1 divided by pi times 2 centimeters squared. So that's just going to be 4. J2 is I2 over pi times 4 squared. This is because these are circles, so I'm using the area of a circle. Of course, 4 squared is 16. J3 is I3 divided by pi times 2 squared, which is 4. And J4 equals I4 divided by, again, pi times 4. Now, the way I'm going to do this, to really label everything consistently, is I'm just going to call my initial current I. So, I know I1 is just equal to I, and so that's over 4 pi. I know I2 is equal to I1, so that is also equal to I over 16 pi. By contrast, I'm going to get these words out of the way a little bit, just so I give myself a little bit of room. I3 and I4 are both equal to half that value. So I divided by 2 over 4 pi, which gives us I over 8 pi, which is the same thing for I4 as well. So just noting that my largest current is the one that I'm dividing by the current density is the one that I'm dividing by the smallest number, then let's see. This should be J1 is larger than J3, which is equal to J4, which is larger than J2. So this gives us a way of building up our intuition for how current behaves and how that relates to current density. Finally, the last note of the day, conveniently almost exactly at the 50-minute mark for our lecture. Here we are considering 3 wires made of the same material. Wire 1 has a certain length and a certain diameter and a certain resistance. We want to know what a resistance does a wire of different length and diameter have. And we're going to do another exercise with the other thing. So we're going to note that all of these are going to be using our resistor design equation. But we'll note if we try to just calculate the resistance of this second wire here by just, say, plugging in our values. So resistance of wire 2 is this times the length, which is 4 meters, divided by the diameter. So area is, well, we're not told this explicitly, but we're given a diameter, so it's safe to assume that this has a circular cross-section. If the diameter is that, then the radius is half the diameter. So this will be pi times 2 millimeters squared. And note right away, we can't solve this because we don't know what the resistivity is. Thankfully, we are told all of these wires are made out of the same material. That was weird. So we can take wire 1 and we can figure out what the resistivity is. I just have to rearrange this slightly to solve for rho. So it's the resistance times the area divided by the length. I am told all 3 of those numbers, or at least I'm given enough information to calculate all of them. And in the interest of time, I'm just going to refer to my results, except we don't do it that way. So what we're going to do instead is we're going to just take this and we're going to plug it right in there. So R2 will be R1 times A1, which is pi times 1 millimeter squared, divided by L1, which is 2 meters, multiplied by 4 meters, divided by pi times 2 millimeters squared. So note when I do that, my pi's cancel out. I plug in 18 ohms for my resistance 1 value. I do my unit conversions and I calculate everything. And when I do that, I get that R2 is 9 ohms. Oop, I'm in the way. That is to say, it is half of R1. Note that you can see this relatively straightforwardly. I get a factor of 2 in the top, but I get a factor of 4 in the bottom. So that works out to 2 over 4, which is 1/2. I encourage you to try the last part of this problem on your own. Check your answers using the notes that are uploaded to the Brightspace, because I have to call it here because I got to go prep for my exam. To that end, I will leave you with the lecture quiz for the day. We have 2 sets of wires that are formed into different shapes, and we want to know the current along the longer path in each one of these cases. So this is going to be using resistivity and the sort of relative lengths of each of these wires. You can assume the wires all have the same cross-sectional area, but the general idea is that you are given the current in one of these, and so you'll want to use a combination of, say, V equals IR, R equals rho L divided by A, to figure out how much current is along the longer path in each one of these cases. So that's this path and that path, given the information you have here. This is not straightforward, but it is just a simple application. Well, it is a challenging application of some of the concepts that we talked about today. So give that a shot. You have till the end of the day to figure that one out, and I will see you all on Friday. Shoot me an email if you have any questions. Set up an office hours appointment. My only thing is that I realize that I am going to have to I will have to block off some office hours time this afternoon because I'm proctoring another exam, so I'm not available for the most part this afternoon, but I am available on Friday. All right, folks, have a good one. I will see you soon. Thanks for tuning in early for today's lecture.